Hello. Okay, you should see the desktop. You should be able to hear me. Let me pop up some windows. Does everything seem okay? Oops. Does everything seem okay? Can you hear me? You see everybody see the desktop?
Yeah,
Yes.
I hear you and see the
Okay,
desktop.
great. Thanks. Okay. So uh click that. Okay. All right. So I finally settled on a date for the exam. Let's see. So your next programming assignment's due a week from today and the exam's a week after that. Okay, so program assignments due the 29th and the exam will be due, the exam will be on a week after that. Okay, so check, yeah, homework on the 29th. Yeah, the homework on the 29th and the exam a week after that. And then here are problems that you can look at. Okay, okay. So the first page are kind of just real general problems, like asking you like, what do words mean? And then the other problems are all very specific problems about answering questions about code. Okay, almost all these problems actually are little programs, and almost every one of these problems you can get the answer from them from the render. Okay, and I point that out in several places where if you with the right options like these are options set to the render. You tell the renderer to do a set debugging in the render, and in the console window it'll give you lots of information. So a lot of the problems you can actually find out the answer by looking at it in the console window. If you do the right, if you type in, well, if you know, take this code and make it a program with these options, you can pretty much see the answer. Okay, so you should check yourself that you can do the calculations, and then you can make sure you know how to do the calculations and make sure you know how to ask the renderer to verify them for you. Okay, so most of the problems can be verified. And if you have questions about the problems, ask me anytime. I think these are good problems just for reviewing the idea of rendering. If you just want to really understand rendering, these are good. These are good general questions to ask about how rendering works. Oh, and the formulas you need are all in the homework assignment. So if you go to the third homework assignment, just remember, if you download the zip file, this formula sheet, the test is really mostly about this formula sheet. This is the main thing, that this is what we've talked about. These are the ideas that we've talked about. So, and you're using them in this homework assignment. All but the homework assignment doesn't use clipping. Clipping is what we've been talking about. So this is what we've been talking about for the last couple of days. The homework assignment doesn't use the programming assignment you're working on doesn't use the clipping at all, but it does use the projection, the view plane, and the pixel plane transformations. But it doesn't. But the homework assignment doesn't use the clipping. Okay. But there are exam problems that ask about using these clipping formulas. Okay. And there's a question. There's a little mention here of colors. We haven't talked about colors yet. The exam is on the first 5 renders, and we'll look at render 5 on next Tuesday. Okay. So on the website, we're going to finish render 3 and start render 4 today, and we'll do render 5 on Tuesday. That's where we throw color into the render. So we'll add colors to the render, and then there's some questions about colors. Okay. All right. Let me think. Anybody have any question offhand? I mean, you have to read these. That you'll have questions probably after you read these. But does anybody have any question right now? Okay. Same with the programming assignment. If you have questions about it, please send me email. It's a little bit of a tricky assignment, especially if you've never done anything that's event driven before. It takes a little getting used to to think about to learn how to think about event-driven programming. Okay, so if you have questions about this homework assignment, please ask. Okay, let me think. Anybody have any questions then? Okay, so let me download render 3 and 4. And also, today we'll probably start talking about render 4, which is about anti-aliasing. So I put some information about anti-aliasing in this rendering zip file, so I'll just download it now. I'm not sure if we'll get to what's in there or not. And you just extract everything. But in this rendering folder, remember, we talked about projection, rasterization, and clipping. So these are folders that have mostly pictures about projection, rasterization, and clipping. And then the next thing we're going to talk about is anti-aliasing. So I added a folder that has some pictures about anti-aliasing. Okay, so that's, oh, and then these are the formulas about the render. They're in here also. So there's the formula sheet. And actually, I even put the tech document in there. If you want to look at how, there's the tech code that creates the formula sheet. Okay, all right. So okay, so the formula sheet's in your homework assignment. It's also in this rendering folder. Okay, now, okay, let's go back and talk about the more or less right way to clip. And it's still not the right way to clip. Now, let me build the Java doc so I can read the kind of the nicer version of the documentation. Okay. Okay. So index, narrow it a little bit. Okay, now go down to the part on clipping. Okay, now remember, you can clip before projection, you can clip after projection, and you can clip during rasterization. Okay, we were clipping during rasterization, and real renders do all three of these. In fact, some do all three of them. They do some clipping before projection, some clipping after projection, and some clipping during rasterization. It's actually, clipping is a pretty big part of what renderers do, and sometimes they mix all three of these strategies. Okay, now we did clipping during rasterization in the first render, and that led to a bad strategy by itself, because if a line stuck real far out of the clipping window, you had a lot of pixels to compute and then throw away. Okay, so you don't want to be clipping a massively long line that sticks out of the rendering, out of the clipping window, and have to walk that line and just throw away pixel, throw away pixel, throw away pixel. Okay, now you can also clip here. Now, if I don't have a picture of that, but if you go back to this rendering folder and you look at projection, that would be clipping on this green volume here. It's like, if we think about it from a point of view what we're saying here, 1 is clipping against this green volume. 2 is clipping against this green square. Or if you want clipping against this window, you project and then clip against that window, as opposed to clipping on these 4 planes that are the sides of that volume. So you can clip in camera space on that volume, or you could project to the front and then clip on that rectangle, or you could wait till you're rasterizing. And if you wait till you're rasterizing, then it'd be a picture more like this. You could, see, I can remember. None of these pictures, I think, really show, clearly show you what we mean by raster line clipping here. Yeah, you would essentially, if the line stuck out here, if this is the frame buffer, but the line actually goes out here, there's lots of, essentially, there's pixels out here, and you have to compute them, but you compute them and throw them away. Okay, that's what we were doing. We were walking that line, and you might just say, when you hit that edge, why not just stop there? Okay, and you could actually, when you hit that edge, stop there. That would save some work. But the problem is, what if the line starts out here and walks towards that edge? If the line starts out here, you don't know where to, you have to walk the line to find out where you're actually enter. So it's actually entering the frame buffer that causes you grief. If the line started out here, you'd have to walk the line till you hit the frame buffer. That would be a lot of pixels to render. Then you could walk across the frame buffer rendering. And then when you hit this edge, you could quit. Yeah, there's, at that point, you're never going to re-enter the frame buffer. So you could quit there, but you'd still have, it wouldn't solve the problem. You can make this half of the line so long that it would take forever to render it. Okay. And if you say, well, somehow you have to find where this line hits that edge and where this line hits that edge, then you're back to basically doing what we're going to do. You're basically clipping not in the rasterization stage, but you're clipping in the middle stage after projection. If you say, well, if this line stretches across here, why don't I figure out where the line hits this edge of the frame buffer and where the line hits this edge of the frame buffer? Then I don't have to rasterize what's out here or out there. Then you're essentially rendering in the view plane. Then you're essentially clipping in the view plane. Okay. Right. So if you're going to clip in the pixel plane, you start at one end of the line, walk it, throwing away pixels, then you hit the frame buffer, then you're rasterizing, putting pixels in the frame buffer, and then if you're smart, at this point when you hit here, you quit, but that still won't solve the problem. Okay. All right. So we want to we don't want to do this one. We could do this one, and there are advantages and disadvantages to this one, and we could do this one. And actually, there's a fourth clipping. There's a fourth one, and that's, I mentioned it the other day. There's clipping in this four-dimensional space called clip space, which is actually what most renderers do. Most renderers actually do a mixture of clipping in clip space and clipping during rasterization. They do this a little bit. Okay, they do this near the edges. They use this strategy on the edges of the window. But instead of doing either of these, they actually clip. Essentially, what it is it's during projection. What it amounts to, the modern way to think of it is not clipping before projection or clipping after projection, but it amounts to a weird idea of clipping during projection, and the projection happens in a four-dimensional space. Okay, so we'll see that a little bit later on, and that's actually the modern right way to to clip. Okay, right. So so we want to talk about this clipping here. Okay, clip after projection. So you're not that. Yeah, that's not the picture. Yeah, you project to this screen, and then you clip things. If something sticks out of this screen, you don't worry about something clicking out of the view frustum. Now that would be step one. Step one would be clipping when things stick out here. Okay, if things stick out here, you go ahead and project them. You still project them to the projection plane, but then they'll stick out of that rectangle. And then you want to clip in that rectangle. Okay, so project first, then clip in that rectangle. That's the strategy we're going to use now. Okay, and that looks like, the pictures look like this. Like you could project the line to this rectangle and the line is in the rectangle. Okay, that's what we call trivial accept. If both vertices are inside that rectangle, which is a couple simple inequalities, then you do trivial accept. Okay, now let's actually start. What we talked about these steps the other day, but we didn't look at the code. So let me also open the code now. And this is where we're gonna, this is where it'd be nice to have multiple windows. Okay, let me. Okay, so here's the clipping stage in the code for the clipping. Okay, and then the documentation is reproduced in here, so it's pretty much, it says the same thing over again. Okay. Okay, here's the actual start of the clipping algorithm. Here's the method that clips all the lines. Well, it clips a line from this model. We'll see it needs to know the line and the model the line came from. So it's clipping the line, but it needs access to the model because it's going to replace some of the vertices in the model. When you clip a line, you may have to replace a vertex in the model. Okay, because you have to shorten the line and give it a new vertex. Okay, so we're clipping the line and we need access to the model. Okay, right. So first, get the two vertices. Yeah, the line segment has an index into the vertex list. Okay, so you get from the vertex list the vertex indexed by the line segment, and you get from the vertex list the other vertex indexed by the line segment. So the line segment has two indices into the vertex list. Now, you don't want to keep typing that over and over again, so store it in a local variable. Store a reference to that object in a local variable. Don't type this over and over again in the code. Okay, but that's one of the vertices, and then there's the other vertex. Okay, now again, get some stuff out of those lines. Okay, there's an x coordinate out of those vertices. There's two vertices. There's an x coordinate and a y coordinate in the first vertex, and an x coordinate and a y coordinate in the second vertex. You could keep typing this over and over again, but that requires more machine instructions. If you're trying to optimize things, you might as well just store those values in a local variable because there's fewer machine instructions needed. I'm not trying to save typing. I don't store these local variables so I don't have to type this. And I don't store these local variables so that I don't have to type this. I mean, actually I do, because reading that's horrible. But it's even more importantly is I no longer have to do all the machine instructions it takes to do all that work. Go to the model, follow the model pointer, follow the vertex list pointer, call that method on that pointer, then follow the ls pointer, follow the pointer to that array in the ls, then get that index number out of that array, then look that up in that list. There's a lot of machine instructions in that line of code. Okay, so you don't want to keep doing them. Okay, so even here, there's a little bit. Here this is follow that pointer to a memory location, then look up that field in the object. Follow that reference, look up that field. Whereas this is just a local variable. This could even be stored in a register. Okay, so this could be this is just going to be way faster. So local variable for x, local y, local x1, local y1. Okay, so make local copies of all the important values you need. Okay, then try to follow the picture with the code. I hate Windows does that. Try to follow the picture in the code. Okay, so check for, step one, check for trivial accept. Okay, what does that look like? Okay, well, the x coordinate of v1 needs to be between -1 and 1. The y coordinate of v1 needs to be between -1 and 1, and the x coordinate of v0 needs to be between -1 and 1, and the y coordinate. So you have the x coordinate has to be, now notice I wrote it, I don't know if I didn't, I wrote it with not this, okay? So if the absolute value of x is greater than 1, you're outside. If the absolute value of y naught is greater than 1, you're outside. So if you're not outside, okay, I could have wrote it the other way. I'm not sure if I'm actually, if I really cared about performance, I would write it this way, write it the other way, compile them, and see which one has fewer instructions. You know, the other way is if the absolute value of x naught is less than 1, and the absolute value of y naught is less than or equal to 1, and the absolute, yeah. I'm not even really sure which one would be better way to write it. Okay. Um, so, but this checks for each of the x and y coordinate of these 2 points to be less than plus and minus 1. Okay, so you're checking for you're in here, and both points need to be in there. Okay, so now if you have trivial except, now here's something kind of odd. You've maybe never seen this before. I return an optional. Okay, here's what's going on. The other possibility is down here. The line segment gets rejected. If the line segment's rejected, you don't want to render it, you want to remove it from the list of line segments. Okay. Now, either the lines, one of three things is going to happen. The line segment's going to be accepted as it is, the line segment's going to be rejected, or the line segment's going to get clipped off. Well, actually, being clipped would be down here. It's going to get clipped off. So one of three things. It's either accepted, rejected, or clipped off. Now, if it's accepted or clipped, it stays in the list of line segments. If it's rejected, it's thrown out of the list. Okay? So what should you return? Now, at one point, I had it returning true and false. When it returned true, it meant kept the line segment. When it returned false, it meant throw away the line segment. Then I changed it to be more modern. It's returning what's called an optional of a line segment. Okay, optional is a real modern idea in Java. Whenever you want it, what this is saying is when you clip a line, you either optionally return a line segment or you optionally return nothing. If you look up what optional means, an optional is either full or empty. It's a container that either holds something or holds nothing. Essentially, it's a really fancy way of representing nulls. It's an ultra modern idea for a better way to represent nothing, nulls. Okay, so the optional class, an optional object, either holds a reference to an object, or it holds a null. Okay. Now, if I'm accepting the line segment, I return an optional of that line segment. So that means the line segment's bundled in the object. So then the person who called this method knows that that line segment is ready to be rendered. Okay, so it's been clipped and it's bundled up, ready to be rendered. So the clip algorithm returns a line segment ready to be rendered. On the other hand, if it's trivial reject, I return an empty optional. The method they call clip sees it got back an empty optional and just iterates to the next line segment and doesn't bother to render that line segment. Okay, so the calling method will call this method with a line segment, and it'll get back optional line segment. If the optional's got something in it, it's the line segment ready to render, already been clipped up and everything and ready to render. If the optional comes back empty, you just say, okay, that line segment doesn't get rendered. That's better than returning a null. You know, like I used to do it, I used to return true or false. True meaning, but then when I returned true or false, there was a problem with, well, where's the line segment that you really want to render? If, you know, what happened to this line segment if I return true here? So the code was a little bit ugly in that case. This was the line segment to be clipped. This was returning true. Where is the line segment that you want to render? Yeah, so I actually had to mutate that line segment. And mutating is kind of like, you know, I'd rather write code that doesn't mutate things. I'd rather write code that returns things. That's the more modern way to think about programming. Don't write code that mutates things, write code that returns the proper thing. So Don't mutate that line segment, return the clipped version of it, okay? But then if I return the clipped version of it, okay, I could return a line segment here. Instead of returning optional, I could return line segment. But then if it's the reject case, this is bound to be a null. But returning nulls is a huge source of bugs in programs. You know, returning nulls is the single biggest cause of mistakes in modern programming. Okay, so Java a couple versions ago invented this idea, and actually Java didn't invent it. Optional. If you Google Java optional, you'll find a gazillion articles about it. It's really interesting. And it was not invented by Java. The optional it came out of functional programming languages. They came up with this idea decades ago, and finally Java and C++ adopted it. C++ also now has optional. I don't remember if they call it optional. Yeah, STD optional. Yeah, they call it, because there's a couple, the functional programming people actually call it, they call it maybe. Okay. Yeah. Why do you think they call it maybe? It's debatable which is a better name, optional or maybe. Why do they think they called it a maybe?
You'll maybe get a reference to an object, or you
Yeah,
may not.
yeah, maybe there's a value there, maybe there isn't. Like here, maybe there's a line segment being returned, maybe there isn't. So in Haskell, this would be written maybe. Maybe you get a line segment, maybe you get back empty. Okay. Actually, I think optional, it's hard to say which is really the better name for it. Uh, Functional programmers are used to calling them maybes, and Java and C++ people are used to calling them optional. Now, actually, optional is kind of weird because it's not an option you have. It's that this guy maybe returned you a line segment or maybe didn't return you a line segment. So optional is, and I can argue that optional is a bad name because it's not an option I have. I'm getting back a value, and that value's either got something in it or doesn't. Okay, so from the callee's point of view, the callee has the option of returning a full or an empty optional. But from the caller's point of view, it's not optional. The caller gets back a thing, and that thing is either empty or full. Okay, so from the caller's point of view, maybe is a better name, because from the caller's point of view, maybe I got an answer, maybe I got nothing. You use this, for example, whenever you look up something in a list. Remember, in like data structures class, you did things like looking up things in a list. What if you search a list for something and it's not there? In the data structure class, you should have talked about that idea. That's super important. What if you have to do a search of a linked list for a word, and the word's not in the list? Okay, here's a good example. Like, here's a famous example of that. Look at the Java string method. Look up the method contains. Okay. No, not that one. Index of. Okay. Give me the index of that character in a string. So look up the character X in dog. What's the answer when you look up the character X in dog?
-1.
Why?
Oh, I'm not sure, because that's not a valid index.
Right. So what are you trying to signal?
It's not there.
It's not there. So you signal it by returning an invalid index. But what if I forget to check that index and then I look up char at my answer?
Null pointer.
No, I can get
Out
a
of bounds maybe.
out of bounds error. Yeah. So if I do something like this, let me here's what you have to think about. What if I do char at index, okay, string dot char at index of x. Okay. Give me the character that's at the, yeah, and actually the answer should be back x. If I ask for the char at, or I could ask for what's next door to the x. So I make it a little bit more interesting. Oops. Oh, just leave it like that. Okay, I should get back x, but I may not. If there's no x in string, I get -1. I ask for the char at -1. Notice that this compiles. See, this compiles even though it's really stupid code, because this thing returns an int and this thing expects an int. But sometimes, what's this thing really telling you? Super important question. Super important question. If a job interview wants to know if you've been following what's going on in modern programming, this is a typical kind of question to ask, because this is getting at the whole idea of optionals. Okay, this compiles because this returns an int and this expects an int. But this thing's saying way more than int. It's also saying what? It's saying two things. What two things is index of telling you?
Well, it's telling you the index of the character if it exists, or it's telling you if it's not in the string.
Yeah, it's telling you two things. It's telling you, one, whether it's in the string or not, and it's telling you, two, where it is in the string, if it's there. Okay. The -1 is blurred with now what it's doing is it's doing those two things with the same data type, and that's bad. From modern programming, that's really bad. Okay. If Java was being rewritten today, they would not have index of return an int. They would have it return a optional, because the optional can hold, it would be an optional of integer, and it would either hold an integer or be empty. And then this code wouldn't compile, because this would return an optional, and this would say, I don't want an optional, I want an integer. This would not compile. Well, if this doesn't compile, what would you be forced to write? They don't want you to write this anymore. They don't want you to write that. They want you to write that, and you get back what?
You'd have to store the reference and then check if it's null before calling char
Well,
at.
no, but you wouldn't check if it's null, because they don't return a null. So you get back a what?
Oh, an optional object, and you
And then you
call
have
the
to check
method.
for what?
If it's empty,
Yes. Then you would say, if result dot empty, if the result is empty, blah, 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 else. Well, the else case is when I can go ahead and do my lookup, and then I would do my lookup by doing something like this. String.char at result dot, I forget what method they do, something like get. You'd get the answer out of the result. So if the result is empty, some kind of error message, you're forced to check for the error case. You want the compiler to force you to check for the error case. You can't write that anymore. If you're using modern Java programming using optionals, now, okay, if you're using modern Java programming with optionals, you can't do something like this. Use an answer that could be essentially saying nothing there. You'd have to call the query method, get back an optional, check if the optional is empty, handle the error case. You're forced to handle the error case now, and then you have the case where everything's okay. Then you get the value from the result and you use it. Okay? This is more code. This is less code. But which is better?
The more code.
Yeah, because it's not allowing you to be lazy and write code that can blow up in your face 2 years later. You can't lazily write code that actually has a hidden bug in it. Notice the compiler doesn't help you here. Sometimes the string returning an integer the integer is actually an error code. The integer is saying I couldn't find X, but you're going ahead and using it. This is horrible. And it took years for the Java people to realize this was really horrible. Now, why don't they go back and rewrite index of to use optional here? Be better, sort of. Why don't they do it?
Probably because a lot of programs are written in such a way
Yeah,
to use
they
the
can't
first
break
version.
25 years of people's code. They're stuck with their bad choices made 25 years ago. This is why old languages get to be a problem. Once we realize that an old language made a mistake, we're stuck with it. Same with C++. Nobody is willing to go back and rewrite the Java libraries or the C++ libraries to use maybes and optionals. All the new Java libraries are written using optionals. So all the new libraries, but there's way more old libraries that are still written this way. Here, let me show you another one where it matters. Let me think, let's see. Okay, there's an index of in list. Okay, what does index of return? Oh, -1 if it's not there. Okay, that was written 25 years ago. If it was being rewritten today, that would return an optional event. It wouldn't return an int, it'd return an optional of int. It uses, first of all, they didn't even have generics when they first wrote Java. Okay, so notice that this is a generic type, optional of line segment. See, it's a generic type. Okay, so you needed generics to be able to do this. So first Java had to invent generics. Guess where they got generics from? That also came from functional programming. People tend to think that functional programming is the wrong way to program, but then all the new good ideas in Java and C++ are coming from functional programming. So first Java added generics about 15 years ago, and then a couple years later, they added the generic optional class. Then they started writing new libraries using optionals, but they can't go back and rewrite the old libraries. They cannot break everyone's code that's written index that's been using these methods like in the list class or the string class. So you see a lot of this now returning -1s, and the other thing is things that return nulls. There's another one in here that returns a null. Not a. I'm trying to remember which one it is. That if it fails, it returns a null. Maybe it's not the list class. I can't remember. Yeah, see this one, if you ask for an invalid index, here's a real interesting question. Get index. How do you signal that that failed? Okay. How did this signal that it failed?
It looks like they throw an exception.
Yes. Okay. How did index of signal failure?
With an integer invalid index?
Yeah. No. Okay. How did index of signal failure of the lookup? How do you answer that question? Somebody asks you, how does index of signal failure of the lookup? And what's wrong with the way it does it?
Oh, returning the same data type as the answer?
Yeah,
Right
it
there?
returns the same data type as the answer, but it gives you an invalid value of that data type, which is really, see, it returns the data type of the correct answer, but it chooses a value in that range that couldn't be a possible correct answer, -1. Okay, but the data type is the type of the correct answer. Very bad. How does my function denote failure? That the line segment couldn't be, that there isn't something to render. This
Empty
thing
optional.
by an empty optional. Okay, an empty optional denoted failure. How does get denote failure?
Out of bounds exception.
An exception. It throws an exception. Okay, so now you've got 3 ways of denoting failure. Notice that they could have returned what here? How else could they have denoted failure?
Return like the default value of the object, like
Uh,
0. Oh
no,
no,
what
no.
would be, well, yeah, but what is the default value of an object reference?
Oh no.
No, yeah, they could have returned null. Okay, well, okay, they didn't really want to return null, so they threw an exception. This should have been an optional. There should, in modern functional programming languages don't use exceptions, because almost everywhere where you would throw an exception, you'd be better off returning an optional, an empty optional. Okay, so if this was being redone in modern Java, they probably wouldn't even throw an exception here. They'd probably return an optional E. They would return an optional E, and then the person calling get checks if there's an empty or non-empty optional object. If there's an empty optional object, it's better than getting an exception. Exceptions are tricky to handle, and also the trouble now is you've got 3 ways of denoting failure. Sometimes you denote a failure by giving an out of bounds, and you return a data type that's the correct data type of the correct value, but you give it a default value. Oh, those are called sentinels. Okay, so what you're doing here is you're returning a sentinel value. So you denote failure using a sentinel value. Another possibility is you denote failure by returning an exception or throwing an exception. Another possibility is you denote failure by returning an empty optional. Empty optional is the best way. And if you were redesigning the language from scratch, you'd probably redesign the language entirely around optionals, like the modern functional programming languages do it. Okay, the exceptions. Right now, Java's got 3 ways. You can sometimes throw an exception, sometimes return an optional, and sometimes return a sentinel value. One problem with sentinel value is that not all objects have a reasonable sentinel value. But if you have it like here, for index of, a reasonable sentinel value is -1. But it's still a bad idea, because it's the same type as the correct answer. So, like I showed you a minute ago, you can write code that's dumb like that compiles, even though there's a time bomb sitting there. At some point, this code's going to blow up on you. Okay, because when you give this guy -1, this guy will throw an exception. Yeah. And then you'll be getting an exception from this guy, but the error really was that, which is maybe not even that big a deal, that there was no X in that string, and you just forgot to check for that. Okay, so that's a little lesson in like modern Java programming. Try to do things, with the no, this has been around since Java 8. So this is actually not even that new anymore. Java 8 was like 5-6 years ago, maybe even 10 years ago. I think maybe now it's 10 years ago. So this has been around a little while. If you Google it, you'll see huge amounts of people who've written articles about it. Lots of really good articles about how to use optionals. They're not as good in Java as they are in languages like Haskell, because they're an add-on to the language. They're not truly integrated into the language very well. So lots of libraries don't use them when they should. Okay, so we saw a minute ago that there are libraries that should be using optional but aren't. See, there are library methods that should be using optional that aren't. So it's not really 100% integrated into the language. So it's better than returning nulls, and it's a little bit better than throwing exceptions. But but you can't use it 100% because if you have to use an older library method like this, you can't use optionals. Okay. The C++ people are doing the exact same thing. The C++ people have optional in the C++ language now, but they have the same problem. Older libraries don't use it when it should. So it's really only available in newer libraries. You're still stuck with it, still stuck with doing the old-fashioned stuff with older libraries using either exceptions or nulls or sentinel values. The old-fashioned way of handling a value that might not be there is either a sentinel value, a null, or throw an exception. Okay. And if you're interested, you can read how. But again, you have to kind of learn the language. But if you learn a modern programming language like Haskell or some of the other functional languages, they designed it from the ground up using maybes. Okay. And so then all their libraries use maybes instead of throwing exceptions. Whenever a function may not return the proper thing, it can return a maybe. Okay. And you can actually even do some interesting things in these languages. Maybe is either a dual thing. Either it's there or it's not there. You can write a function that can return either an A or a B or nothing. You can return a triple. You can return either an A object or a B object or a nothing object, an empty object. Okay, and those are called ethers. You either for return it's called an ether. Okay, the idea with an either is I can say, oh, I'm either going to give you an A thing, or I'm going to give you a B thing, or I'm going to give you nothing, which is the error case. Okay, so an either is like a multi-valued maybe. Maybe gives you either a thing or empty. Either can give you any number. You can actually design your either to have as many things as you want in it. Okay, notice it falls under error handling. Okay, so modern functional languages have taken this idea and really run with it, and you can write pretty elegant code in these languages, without having to deal with nulls and without having to deal with exceptions. You have like one idea, this maybe and either, that can handle all kinds of error conditions. All right, So there's a nice example of a little bit of modern coding. The clipping algorithm is either going to return where is it? Oh, I've lost all my windows. There. The clipping algorithm is either going to return a clipped line segment or it's going to reject the line segment. So in the case of rejecting the line segment, it returns an empty optional. In the case of, oh, the line segment's fine, it returns an optional of that line segment. Okay. All right. So now there's the opening two cases of the method. Okay. Those the trivial accept or the trivial reject. Okay. Now the third case is to actually have to clip. Okay. You don't have a trivial accept or you don't have a trivial reject. So now you go into the clipping stage section. Okay. Now clipping, go down here. Clipping is done one line at a time. You clip on that line. Now in this clipping algorithm, I clip on that edge first, then on that edge, then on that, oh no, let's see, I can't see. It's x equal 1 first. Oh, yeah, x equal 1 first. There's two cases because I could have either v0 or v1 on the wrong side of x equal 1. So there's like, see, it's either the v0 is on the wrong side of 1 or v1 is on the wrong side of 1. So I have two cases to check for. Either this could be v0 up here, or this could be either v0 or v1 up here. So there's two cases to check for. So that's line x equal 1. Then you go to line x equals -1, this line over here. but there's two chases to check for. The guy on the wrong side of x equals -1 can either be v1 or v0. So there's two cases here, okay? Then after that, then it goes to, after the two cases of x equal 1, two cases of x equals -1, then there's two cases of y equal 1. So then it does this line third, okay? Checks, okay. Now, notice that these are mutually exclusive. So when you've checked this edge here and you clip to that edge, you don't check this edge next. That would be if these were ifs without the elses. Then you would fall from if to if to if. These are else ifs, which means as soon as you found a clipping thing to do, as soon as you found something to clip, you're done. You don't do any of the further tests. And the idea is that after you've clipped one time, notice that each one of these is a recursive call to new clipping. See, every one of these cases is a recursion. Once you clip that line there, just start the whole process over again on that clipped line, okay? So call clip recursively on the clipped line segment. See, there's the clipped line segment. Notice I'm not mutating the original line segment. I'm returning a new line segment that is clipped. So I'm trying to do this in a very modern style of programming. Instead of mutating things, always say, well, build a new thing that holds what I want to return. Don't mutate this guy. Try to avoid that as much as possible. So instead of saying, oh, I'm going to take this line segment and shorten it, I don't really do that. What I do is I build a new line segment. Okay, and that new line segment has one old vertex and one new vertex. So I reuse one of the old vertices from the original line and I build a new vertex. So here's the old vertex that was being reused, and here's a method call that interpolates a new vertex. So build a line segment using one new vertex and one old vertex. So I recycle an old vertex. No, I'm not mutating the old vertex, I'm recycling it. I recycle an old vertex, build a new vertex, and bundle them into a new line segment. Notice that this was chopping off V0. So the new vertex is where V0 was. See, this other case, I'm chopping off V1. So the new vertex is in the place of V1 and I'm reusing V0. So that's why I have to check whether it's V0 or V1 that's over here. So that's why I have to check if it's V0 or V1 that's over here. Because if it's V0 over here, I replace V0. If it's V1 over here, I replace V1. Notice I end up with kind of messy code. I really don't like this. I really wish I could come up with it. If you look at this, this should raise real questions in your head. Does anybody see like why I would be really, what is it about this code that makes me not real happy?
It's repetitive.
Pardon me?
Repetitive?
Yeah, it's almost 100% repetitive, but not quite repetitive. Like here, the recycled vertex is in the second position. Here, the recycled vertex is in the first position. Here, I'm saying, I'm printing a little error message, clip off V1. Here, the error message clips off V0. But, how can I not repeat myself here? I could write some really hairy method that took all kinds of parameters about, oh, what do you print here? And do you put the new vertex here? Or do you put the new vertex here? When you put the new vertex here, do you use that index? Do you use that index? I could try to write some really complex function that replaces this block and this block. And I think this is a good example. If you read about the dry idea, don't repeat yourself. There's this idea among programmers of dry. Don't repeat yourself. See, I had to scroll down a little bit. Don't repeat yourself. There's a lot of people point out that you can't take that too literally, sometimes repeating yourself is better than the alternative of not repeating yourself. And I kind of think this is one of those cases.
Is it because of readability?
Well, the this is not very readable either. Yeah, it's a tough issue. Like a really hairy method that would replace each of these blocks could be itself very unreadable and hard to maintain. On the other hand, these blocks are kind of hard to read and hard to maintain. I have not found a good answer to this yet. Right now, I prefer leaving them like they are, not trying to wedge them into a single method that somehow handles all the little differences between these. And there's a lot of these. There's 8 of these blocks because there's 4 line segments, left edge, right edge, top edge, bottom edge. And for each edge, I have 2 cases. Either V0 is on the wrong side of the edge or V1 is on the wrong side of the edge. So I've got 8 cases here that, unless you look carefully, they all look real similar. But there's little differences everywhere. This one says clip off V0. This one says clip off V1. This one says clip off V1 at Y equals 1. This one says clip off at X. And so there's all kinds of little differences between every block is a little bit different than every other block. There's no actual repeated blocks. But trying to find a method that replaces one of these blocks, I thought it was maybe better to leave them repeated. But that might, but somebody else, especially if somebody comes up with a clever way, maybe somebody can come up with a clever way of abstracting that chunk of code into something that's not too ugly. Every time I tried it, I thought it was better this way. Okay, but as a programmer, what do you look for? If you see repeat, 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 you think, don't repeat yourself. But at the same time, if you read what people read about don't repeat yourself, you'll see them say, but sometimes you're better off kind of repeating yourself than trying to shoehorn too many cases into one method. You don't want methods with 7 or 8 parameters. That might just get to be too messy. Okay, so right now this code is not elegant, but there is a definite pattern to it. So if you study it, you can see what the pattern is. I'm building a new line segment that uses 1 old vertex and 1 new vertex. So it's always 1 old vertex, 1 new vertex. 1 old vertex, 1 new vertex. The new vertex is the one being replaces the one being cut off, and the old vertex is the one that stays. Okay, all right. And then I have a little error message that tells me that for debugging purpose, that lets me see what's happening. I'm cutting off the V0 on that edge. So I want to say which one I'm cutting off on which edge, which one I'm cutting off on which edge. It's real nice to have that error message printed out when you want to see the debugging stuff. So without that line there, it would be a little bit easier. There'd be less variation between these. But having that logging message there is useful. So the logging message becomes part of the difference between these blocks. Okay, so then this repeats over and over 8 times. And then I did a little else here. I could have done no if here, because that last case should be the default case. But I did a thing where I kind of like to do it this way. I don't want a default case here. I want to check all 8 cases. Then I have an else that says we should never get here, and then throw an exception. Believe it or not, I've landed here many times. How would I land here? Why do you think I like it better to not just say, oh, this guy's a default case, so you don't need that? Logically, that's fine. Why would you think I might prefer this? This is a good thing to think about. Why would I prefer this? Why would I have this? We should never get here.
Catch exceptions.
Pardon me?
To catch any exceptions.
Well, no, there shouldn't be any. I should never get there. Logically, my program, the logic of my program is if I didn't have any of those other cases, this 8th case is a default case. I have to have one of those 8 cases. After I've checked for the other 7, This is the last one. So why did I prefer not to write this? Why did I prefer to check for the 8th case and then say, well, I should never get here, but if I do get here, throw an exception?
Just good practice in general.
Pardon me?
Just good practice in general.
Why? What's good about it? What am I'm trying to solve a problem by doing this. If I delete that and delete that, the code is correct. But I don't like it as much. This is also correct, and I like it better. They're both correct, but I like this one better. The hint is, I have landed in there. Here's another hint. Humans are fallible. Yeah, okay, somebody wrote, to find bugs in your code. Exactly. The key is that I could goof up one of these cases. When I was writing this code, there were bugs all over the place. And it was way better to get this thing thrown in my face to end up in this case accidentally. Okay? See, if I delete this and delete this, logically, yes, it's equivalent. But if I've actually made a mistake somewhere, I could end up in this case pretending it's the correct case when it's really not the correct case. Okay? I'm more likely to realize I made a mistake if I get an exception thrown at me. Okay? This is more likely to show me I made a mistake. The exception's thrown in my face, as opposed to, boy, why did that line clip real weirdly? See, if it was the other way, I might have a case where some line clipped in a bizarre way, and I have no idea why that line clipped in a bizarre way. And I may not even notice for a while that one of my lines is clipping in a bizarre way. Whereas if I've got something goofed up here, and I should be in this case, but somehow reason maybe I got my logic wrong here. Yeah, maybe I messed up my logic. I should have been up here, but instead I'm falling into here and I'm clipping a line in a weird way. On the other hand, if I do this and I've got some logic goofed up here, then I will fall into this one and I'll get a big error, a big clipping error saying you should never have gotten here, so go figure out what you did wrong, as opposed to some subtle error where some line segment's clipping in a weird way, and I don't understand why that line segment clipped in a weird way. Okay. When you have mutually exclusive cases, you always have the option of making the last case the default case. You can always make the last case the default case. But then you're assuming that you did all your checking right, so that when you fall into this case, you really belong in that case. The other option is to do all your mutually exclusive cases and still have a default case, but the default case just throws an exception. Okay. Not everyone likes this idea. Some people say, no, you should write the code correctly. You should, it should be like this, and you should not have any errors in it. But especially when you're first developing the code, it's nice to have these little catches. This thing that just says, you shouldn't have landed here, but you did, is actually kind of sometimes real useful. Okay, so I have 8 mutually exclusive cases. I could just make the 8th one the default case, but I don't. I make the 8th one, I test for the 8th one just like I test for all the others, and then I have then I have the little catch-all that says we should never get here. You'll see these in my code pretty often. These little, an else clause that says we should never get here. And it's always the same thing. Mutually exclusive cases, but instead of letting the last one be the default case, which is logically correct, I go ahead and check for the last case. I check for all the mutually exclusive cases, and then make this one essentially a catch-all that catches errors. Okay, all right. So notice that one of the things I hope you're seeing is how to think about style of coding. how do you how do you solve general problems? What are good coding practices for solving general problems? You're starting to think in terms of design. How do I design things? Not just get the right answer so I get as many points as possible, but like, how do I write code so that my boss doesn't grumble? That I'm not causing grief for someone 3 years from now who has to maintain my code. How do I write code that I can read myself a year later? I don't know, how many of you have ever gone back and read something you wrote a year ago? Probably you don't do that very often because you do mostly homework assignments. Go read something you read a year ago. I guarantee you'll hate the person who wrote the code. Everybody knows that. You read something you wrote a year ago and you go, what idiot wrote this? Okay, that's almost everybody's universal answer question to reading their own code. Because first of all, you have trouble reading it. You realize where you made little dumbest choices. Okay, it's real instructive to read your own code a year later. So then you start writing code to try to solve those problems. How do you write code in a way that's robust, that's readable by other people, that's maintainable by other people, where you can figure out what it's doing a year later, things that help you find bugs, little tricks to help you find bugs. Then also modern things like the optional, like saying, oh, I can use a modern idea. I can use a modern idea to make my code better. Okay, so modern ideas, good practices, try to see where you can write things better. And then, then like, okay, lots of repeated code, real debatable issue there. Real debatable. Should that be left like it is, or should that somehow be refactored? And that's one I think people can. I think someone could probably make a good case that I should refactor this. 8 blocks of code that just are minimally different. Maybe they're good. Maybe it's a good idea. Maybe it's not. Maybe it's not a good idea. Okay. Now, here's the thing that does the interpolation. Okay. So if we go back to our overview, here were the equations that compute where the clipping point is. Okay. And here's the code that actually, so that's in this interpolate. This is where the lerp is. And these formulas here, like there is there. Okay. All right. Now there's 4 versions of it because there's one version for x equals 1 line, one version for the x equals -1 line, one version for the y equals 1 line, and one version for the y equals -1 line. Again, kind of repetitive code. Yeah. Should I write something really abstract and just have one formula? Or is it better just saying, I got 4 cases. Clip on that line, clip on that line, clip on that line, clip on that line. Okay. Again, kind of, don't repeat yourself except when repeating yourself is okay. Okay. So yeah, it's not it's really, the more you read, first you'll read everyone saying don't repeat yourself, and you'll say, okay, you should never repeat yourself. Then as you continue reading, then you'll start seeing the articles where people say don't repeat yourself except when you should repeat yourself, because then you start realizing that sometimes it's just not worth the effort not to repeat yourself. Okay, so there's some repetitious code there, and that's just 4 versions of this formula depending on whether it's the line x equals 1 I'm clipping on, or the x equals -1 I'm clipping on, or y equals 1. Okay, so then I get the t value, and then I need to plug t into the y value or the x value. That is done down here. Okay. Okay. So then I compute the new x and y for the clipping point. I compute the new x and y coordinates. Okay. So the explanation of this algebra is over here, and the actual code for it is over here. And I tried to make the code kind of match the notation I was using over here. So I tried to make the code kind of match. Okay. So then there's lots of logging information. Like when something's clipped off, remember the idea of clipping was you're going to travel from here to here. At time 0, you're here. At time 1, you're here. You're trying to figure out at what time do you cross that line. And then, so that's this solving for when do you cross that line. Now, the way to think about it is when you're traveling like this, there's really two motions. Your x-coordinate is moving horizontally, and your y-coordinate is moving vertically. Concentrate on just the x-coordinate. As the x-coordinate travels horizontally, when does it hit this point here? That's what this thing does. See, this just says, oh, let's look at just the x-coordinate. As the x-coordinate moves horizontally, when does it hit 1? Okay. Now, if I know when x hits 1, then I go over here and say, okay, now y is moving vertically. Where is y at time t when x hits 1? So as x is going here, I find when it hits 1. Then I use that t in the y-coordinate and say where y is when x hits 1. So then after I found that t, I say, now I switch to the y-coordinate and say, oh, y is moving up. Where am I at the time when x hits 1? So when does x hit 1? Where is y when x hits 1? When does x hit 1? Where is y when x hits 1? And then you find that point there. Calculation you'll see over and over and over again, all over the place in statistics and probability theory, machine learning. This is the linear interpolation problem. You'll just see this calculation. There's the key idea. At time 0, 1 minus 0 is 1, 1 times v naught. At time t equals 0, 0 times v naught 1 is 0. So at time 0, I'm here. At time 0, I'm there. At time 1, well, 1 times v1 is v1. 1 minus 1 is 0, so there's no v0 left, so I'm just at v1. At any time in between, I'm actually taking an average of this and this. The reason you see this in statistics is because this is an average. I'm averaging that point and that point with different weights. So it's called a weighted average. The average is t weight on this guy and 1 minus t weight on this guy. So when t is close to 0, more weights on him than on him, so the average is closer to him. When t is close to 1, more weights on him, less weights on him, so when t is close to 1, the average is closer to him. So the LERP formula is also called a weighted average formula, and it's everywhere in machine learning, data science, statistics, probability, computer. It's used a lot of places in computer graphics. We'll keep seeing this formula appear over and over again. We're going to use it over and over and over again to solve problems in graphics. It's such a useful formula. It just solves so many little problems. It's got lots. You can call it weighted average. You can call it linear interpolation. People call it LERP. Some people call it in-betweening because you want to know what's in between here and here. Some people call it the morphing equation. Yeah, when you see one figure morph into another figure, that's done with this formula. We'll look at that later on too. So if you want to morph a circle into a square, or if you want to morph one photograph into another photograph, that's actually done with this formula here. So it's called morphing formula, in-betweening formula, LERP formula, linear interpolation formula, weighted averages formula. It's got a ton of names because it appears in a ton of different places. Okay, all right. That's all the ideas. I think that's all the ideas in the clipping algorithm. Let me show you one last thing, how the pipeline package handles this. We want to pass a model through the pipeline. And what we're going to do is take a general point of view that each stage takes in a model and doesn't mutate the model. It gives us back a new model that holds what we want done in it. Okay, so projection stage takes in a model. The vertices are in camera space. The model I return has all the vertices projected into the view plane. So this is the version of that model where everything's been projected. I don't want to mutate that model. I want a new model holding the new vertices. Then what does clip do? Clip takes in a model, and it gives me back a new model. What's in that new model? Well, now the vertices are been not modified. It's the line segments that have been modified. This model holds new line segments. Now, if a line segment didn't need to be clipped, it's just in here, just like it was in here. If a line segment from here was trivially rejected, it's not even in this model anymore. And if a line segment in here was clipped, it's replaced in here by a new line segment that is the clipped version of what was in here. So I have this, I'm using a general metaphor that each stage takes in a model and gives me back a new model that holds the data I want. I don't mutate anything. I try to do as little mutation as possible. I want the stage to give me back a model that's a new version of what that model was. So it's a new version. Later on, we'll see interesting things. If I want the render too, it can return this model. And you can do really interesting special effects by telling the renderer, render this model for a few stages, then give it back to me. And you can do all kinds of weird things with mirroring effects and real interesting effects by telling the renderer, partially render this model, then give it back to me. So we could return these models to the graphics program. Okay, so this is a nice metaphor for how this thing's going to work. Of every stage taking a model and give me back a new model that's been updated to be whatever that stage is supposed to do. Okay, all right. So we run out of time. If you have questions about the homework, let's see where. So if you have questions about the homework, let me know. And if you have questions about the review problems, let me know. Talk. Work on the review problems. They're review problems. It's not the exam. So if you ask questions about them, that's fine. If you talk to people about them, that's fine. Work on the review problems. And we didn't get to render 4. We'll start render 4 and render 5 next week. And that's going to be anti-aliasing and colors. And again, we're going to be doing lerping. 3 renderers in a row use lerp. Renders 3, 4, and 5. 3 renders in a row are based on the lerp idea. The clipping is based on lerp, anti-aliasing is based on lerp, and colors are based on lerp. 3 different uses of lerp in 3 renders in a row. Okay, so we'll quit there. So again, any questions at all, please write. Please come to office hours if you have questions. And I'll go ahead and have a nice weekend. And I'll end the meeting now. Okay, bye-bye.